Rock stress measurement. In combination with rock properties, rock stresses affect the way in which rock masses deform. This deformation may be required to be small, as in a rail tunnel. Deformation may need to be large, as occurs in mining using caving techniques, or as occurs in the collapse of a longwall goaf. Rock stress is also a key to understanding rock bursting and other larger seismic events. Rock stress measurement is one of the key measurements required in determining rock mass behavior. Its measurement is, however, not trivial. There are several approaches to its measurement. These may be roughly separated into in-hole tests, which include overcoring, hydrofracture, hydrojacking, borehole breakout, hole ovality measurement, and the measurement of shear wave velocity with a rotating dipole sonic tool. Tests on core include core ovality, post-elastic recovery, deformation rate analysis, and the Kaiser effect. All these methods are indirect and therefore less certain. It is also useful to examine the geological structural features associated with the effects of stress to get an understanding of the stress history of an area. SIGRA uses the process of 2D and 3D overcoring, hydrofracture, hydrojacking, borehole breakout, core ovality, and the examination of geological structures in its analysis of rock mass stress state. These methods are frequently used in combination to obtain as broad a view of the stresses as possible. Overcoring is a process by which stress is relieved around some device that measures rock strain or deformation. The common process is to overcore around a pilot hole containing an overcore cell and to measure the deformation as this occurs. This video shows the SIGRA IST 2D cell being set into a pilot hole drilled ahead of an HQ core hole. The core barrel is then lowered and overcoring takes place to relieve the stresses on the core, while the pilot hole deformation is measured. The SIGRA IST 2D tool can be used without glue, but deriving the three-dimensional stress state by overcoring requires the cell to be glued into place. This slows the process. The core and stress tool are then recovered together. The analysis of overcoring is dependent on the rock properties. It is simple if the rock is isotropic and linearly elastic. If the rock is anisotropic but linear elastic, then analysis is possible and simple provided that the anisotropy is axis symmetric with the core. If the anisotropy is not aligned with the core, its analysis is possible but more complex. Many rock types are non-linearly elastic, and the Young's moduli and Poisson's ratios depend on the state of stress. If the rock does not behave in an elastic manner, then overcoring is not a suitable rock stress measurement system. When the core behaves in a nonlinear elastic manner, analysis is possible but more complex, requiring careful measurement of the rock properties and numerical modeling using finite element methods. A good overcore requires an elastic rock response and no borehole breakout within the pilot hole. Hydrofracture involves pressurizing a borehole until a tensile stress is developed at the borehole wall with subsequent fracture propagation. Hydrofracture is usually achieved by straddling a zone in a borehole using packers. These must be inflated to a wall scaling pressure that exceeds that of the hydrofracture fluid. As a consequence, the packers may initiate failure. SIGRA manages this by keeping the packer pressure just above pressure of the injecting fluid. The measurement of rock stress through hydrofracture requires sealing a section of the hole and pressurizing it until a fracture is created in the borehole wall, then propagates. Fluid injection is then stopped and pressure decline takes place and the fracture closes. The process is normally repeated by pumping again and reopening the fracture. The normal analysis of hydrofracture is based upon measuring the closure pressure of the fracture as an indication of the minimum stress level. This is determined by careful analysis of the pressure decline after pumping ceases. Frequently, several sequential fracture closures may be determined. These may be related to fracture rotation or pre-existing fractures within the rock mass closing in sequence. The major stress is difficult to determine from hydrofracture. Most hydrofracture analysis is based upon the axis of the borehole being aligned in the plane of the minimum principal stress. It also relies upon the assumption that the rock behaves in linearly elastic manner and is homogeneous. These are conditions that are frequently not met. The direction of fracture propagation would normally be perpendicular to that of minimum principal stress, provided the rock is homogeneous. Where fractures or planes of weakness exist in the rock mass, the hydrofracture may extend into these structural features. Where the minimum principal stress is not coincident with the axis of the borehole, then the fracture will rotate from the borehole wall into this direction. However, there is no way of measuring what this direction is. The fracture orientation is usually determined by the use of an acoustic televiewer scan before and after the hydrofracture process. This may show the orientation of the fracture that is created. An alternative to the use of the acoustic televiewer is the use of impression packers that show a trace of the fracture in the borehole wall. An alternative to the use of packers is to cement tubing into the borehole and to fracture the zone below it. Doing this changes the stress situation in the borehole, as the cement plug can impose upward force on the whole wall. It also practically prevents the measurement of the fracture direction. If the rock mass is fractured, it may be possible to use hydrojacking to measure stress across a joint. This involves using packers to straddle a fracture within a borehole. This straddle zone is then pressurized until flow indicates a fracture has opened. Pumping is then halted and the pressure decline within the hole is monitored. Fracture closing is determined by similar processes to that used for hydrofracture analysis. If several fractures of different orientation can be tested, it is possible to build up information on the stresses in different orientations and to obtain some bounds on the possible stress tensor. More usually, there are multiple fractures within the straddled zone, or intersecting fractures, so that multiple closure pressures are detected in the pressure decline, and there is always uncertainty about which fracture set is closing. Borehole breakout. The drilling of a borehole within a rock mass induces stress concentrations around the borehole wall. Where the rock is sufficiently weak, compressive failure of the borehole wall may occur. This breakout usually occurs on the borehole wall perpendicular to the major stress direction. In situations where highly directional stresses exist, it is sometimes possible to see a tensile fracture development on the borehole wall in the direction of the principal stress. The image to the left is of breakout in sedimentary rock and shows a fairly even breakout trace. The image to the right shows breakout in a metamorphic rock. Here the breakout is frequently less even. Borehole breakout is a direct indication that problems with rock failure will occur on excavation. More detailed analysis of stress from breakout requires additional information such as might come from the minimum stress measured by hydrofracture and the compressive strength of the rock perpendicular to the hole axis. Determining this compressive strength is difficult to achieve with certainty, and it is generally better to treat borehole breakout as an index of stress to strength ratio that also provides information on stress direction. Core ovality. If the measurement of core diameter is made at sufficient accuracy, the difference between the major and minor diameters can be determined. Using this information and simple elastic analysis, it is possible to derive the difference between the major and minor stresses perpendicular to the core. For this system to be used, it is necessary to avoid regrinding the outside of the core after it is cut. If, however, the core bit is conical and expands inwardly so that this regrinding does not take place, the core ovality is preserved. The key to the use of core ovality is a suitable core bit that will not regrind the core and a precise measuring system. Interpretation of rock stresses. Most stress measurements are point measurements within a borehole. What is needed is some means to interpolate the stress situation between these points of measurement. Where borehole breakout exists, it provides an index of rock stress over rock strength over a length of the hole. Core ovality may also be used to determine the difference in rock stress over the length of the hole. It has the advantage that it does not require the rock to break out. This must be based on a model of rock behaviour and history taking into account the effects of temperature and faulting. In a sedimentary environment, the concept of tectonic strain has been found to be useful in interpolating between measurements. Tectonic strain is the strain that has been imposed upon the rock mass to generate the stresses that exist therein. Here we have monotonically changing strains. However, the stresses vary widely depending on the stiffness of the stratigraphy. Here is an example of the tectonic strains around the Bulli seams in the Sydney Basin. SIGRA provides interpretations in more complex geological environments. This shows the changes in stress below 600 metres relative level, where complex faulting causes the stress to change direction and magnitude several times within 1 kilometre lateral distance. Examinations of dips in the stratigraphy derived from acoustic televiewer images showed that multiple faults exist in this area.